Once again, here we are in the PLC Professor's workshop, lab, project development, all of our hardware. And this next lecture that we're going to do is relevant for any of the platforms supported by the Logix engine, whether it's RSLogix, which I haven't seen in years, Compact Logix, Control Logix, Soft Logix, etc. And the subject is data types. One of my favorite subjects because the number of different data structures, data types, information object modeling is just amazing. In the 500 micrologix realm, you really only had a couple of data types and they were mostly integers. And everything else was made up of 16-bit integers. With Control Compact Logix, you have at least 5 or 6 atomic data types. If you want to call a Boolean, a bool is an atomic data type, but it does take up 32 bits in memory. So it uses one 32-bit dent, and it uses 1 bit out of those 32 bits for the storage space for that variable pointer tag that's a bool data type. So although it uses 32 bits, it's still a single bit. It's a Boolean data type. Then there is single integer, integer, double integer, and real. Those are the basic atomic data types. Since then, they've expanded and there's a few more. We're not going to get into those. Those are the atomic data types, meaning they are the atoms that all the data molecules are made out of. So the timer, counter, alarm, variable frequency drive, there is a data type for everything. So let's get into this lab project and look at some of these data types. Welcome back. This is another lab discussion video that supports an introduction to RS5000 Volume 1. This is the first volume of the complete PAC Learn series. The lab projects for data types can be found approximately on pages 140 through 152 of this manual. Specifically, we're going to be talking about data types. We're going to discuss the lab projects that you did in one of the later labs in Volume 1. When I say data types, I mean data types, not information types. If you think about the difference between data and information, information implies some reasoning or a correlation of data. So we're talking specifically data types. Whereas all data is stored in binary form in the controller's memory, in the memory array, typically as an array of 32-bit double integers, or dents. The actual data type is inferred by the creator of the data table that will eventually be downloaded from RSLogix 5000 into the controller's memory. It will serve you well to keep the idea of data and data types in perspective anytime you are interfacing with a programmable logic device such as a PLC or a PAC. Most of the data types that we will be discussing are data structures, or better said, structures comprised entirely of data. If you like, you could say that these data structures are data molecules, and the data molecules, as you know, molecules are made up of atoms, so you have atomic data types. There are only a few specific atomic data types that make up these data structures. Now in RSLogix 5000 they do call them atomic data types, but they don't call the structures data molecules. But they did grab that moniker of atomic data types, and so I'm just expanding on it. There are categories of data types as seen in the controller organizer of RSLogix 5000 or the Logix Engine. That's what you're looking at right here, is a little screen capture from the controller organizer. The controller organizer, and this is just a small part of it, the controller organizer is to the controller what a filing cabinet is to an office worker. That is, to someone who follows directions, a list of instructions that require referencing data in a file and then generating new data or conclusion data based on the values of the reference data. If you open, that is expand, the folder data types, as you see here, you will see 5 subfolders. Now, I've never seen data types not expanded, but you can collapse data types by clicking on the minus sign. So the fact that there's a plus sign there, a minus sign, means that there's subfolders. If you expand data types, you will find 5 subfolders as seen here. As you already know, any folder in the controller organizer without a plus symbol in front of it is an empty folder or an empty category. To keep things simple, we will start with predefined data types. If for no other reason, then they are the basic components for anything that you have the capability to create in RSLogix 5000 for the Logix Engine. The list of predefined data types represents what is available in version 20 of RSLogix 5000. So in earlier versions, some of these weren't available, and in versions to come, 21, 22, and so on into the future, you will see a few more added on occasion. In particular, alarm analog and alarm digital may not have been there in the beginning, but most of these have been there for quite some time. This list of predefined data types, as I said, represents what is available in version 20 of RSLogix 5000. Now, these are not atomic data types, but this list includes the atomic data types. The smallest of the atomic data types is the Boolean, or bool, B-O-O-L, data type, and it is stored as a double integer with only bit 0 of the double integer exposed for use. That means if you define a tag as a Boolean, not define it as a bit of a dent, which you could do that. You could declare a dent and give it a name bits, or we'll say bits 0, and define it as a dent and then use the individual dents. I'm saying that if you define your tag as a bool, you have consumed a 32-bit double integer in the controller's memory. It behooves you to not create too many bools. Memory's gotten pretty cheap, so I don't think memory size is going to be an issue, but there's some other efficiencies involved in communications. The next larger atomic data type is the single integer, or cent data type, and it is stored as a dent, double integer, with only the least significant byte of that double integer exposed for use. So if you define a tag as a single integer, you have again consumed a 32-bit dent in the controller's memory. Now, the fact that we said least significant bit, least significant byte, doesn't mean that you have access to the rest of it, because you don't. I'm just saying that's all that's exposed if you define your tags with these atomic data types. And then, of course, we have an integer. And, of course, you know, an integer is 16 bits. So that's the least significant, the 2 least significant bytes of a dent, which would be bit 0 through bit 15. And again, if you have defined the tag as an integer, then you have used up a 32-bit double integer in the controller's memory. And then, of course, you have double integer, which we talk about a lot. This is the native data type to the controller's memory array, and a dent is a dent, no more, no less. It behooves us to use dents. The word was behoove. Occasionally I get comments, and I think it's sometimes I use words that aren't common. But anyway, it's a benefit to you to use dents, double integers, as often as possible in your data structures, especially if the data is going to travel out of the controller to other controllers or devices over the network of the backplane. Because if you define a tag as a Boolean, before it can go on the backplane, it becomes a dent, and it's sent as a dent. You can't send 1 bit across the backplane. You send a dent. And then, of course, we've got real, which is floating point, and it's 32-bit IEEE. If you're curious about the actual format, go on the web, type in IEEE 32-bit float, and it'll give you all the details on the format for that. But so you have floating points, 32-bit IEEE. And then of course you have long integers. Now that's a newer atomic data type that was not there in the older versions of RSLogix 5000. This is a 64-bit integer value used to store alarms and events time tags. Only limited instructions will support using long integers. The instructions that do support long integers are get system variable, set system variable, copy, and CPS. Only wall clock time object is required to support the long integer data type. So the wall clock time object, when you use GSV and SSV, it is required to support the long integer. Passing of long integers to an add-on instruction, a JSR, as a parameter or subroutine or a return is not supported. Long integers are not supported passing in and out of add-on instructions or in and out of subroutines. Aside from the atomic data types that we just mentioned, the remainder of these data structures were specifically created to support instructions. They're called backing tags. So what you're looking at here are many classes of data objects. These aren't actual data objects, they are classes of data object. Although you can create an instance of these data types, you would not ordinarily do so separate from defining a tag name in association with an instruction that will then execute with that same data structure. So ordinarily you don't go in and create a tag and use these data types here. Now the atomics you do, but the others typically you will create an instruction and then put a tag name in associated with that instruction and define it. It will be defined. For instance, like a timer. If you bring up a TON, TOF, RTO, and you type in delay timer, you right click on it, it says new, it is automatically going to want to make it a timer data type because it knows it's a timer instruction. So these are backing tags for the most part. For instance, a control data type that you may have used in RS500 land with RSLogix 500 with sequencer instructions is a predefined data type that was available in RSLogix 5000. If you create an instance of this data type without an instruction, which in RSLogix 5000 you could create, a couple hundred timers or a couple hundred control tag structures without actually using them in instructions. So you don't have to create the instruction to have the tag. You can create the tag and then create the instruction. If you create the tag without any instructions, that would be kind of like someone handing you a sheet of paper and stating, here's your dog that you bought at the pet store. And then you look at this sheet of paper expecting to see instructions to go pick up the dog. And what it says on it is, one tail, two eyes, one nose, two ears. It barks. It may wag its tail. It may slobber on you. It may poop in your yard, on your carpet, and it may annoy the neighbors, on and on and on. This is not a dog, but a rudimentary data structure to describe the dog. The dog has a collar, it has a height, it has a weight. This is just a data structure. Now, you're more likely to have encountered, previous to today, a counter data type. And this counter data type is an exact match for what was in RSLogix 500. And if you look at it, you have a preset, an accumulate, count up, count down, done, over, and under. So again, you can create many instances of the counter data type, but until you actually execute a count up or count down or reset instruction against that data structure, you really haven't done much. Notice that in the list of members here, there are no members that say CTU, CTD, or RES. So count up, count down, and reset are not members. They're not tags. They're not data. They are instructions that execute against this data structure. These data structures actually are methods as well, but that's a story for another day. So I think you get the point here. Here's another predefined data type for using for timers: preset, accumulate, enable, timer, timing, and done bit. So this is actually a timer. Now what you're looking at here is not a timer. It is describing the class of objects defined as timer. So if you go in and create one and it's called time delay, and that's what you name the tag and you define it as a timer data type, within there you'll have 2 double integers and 3 booleans. Now those 3 booleans aren't going to take up 3 dents, because in the data structures created as predefined data types, they will put all 3 of those bits into one word, but you're going to have at least 3 dents used up. And what's it say there? 12 bytes. How many bytes in a dent? 4 times 3, that's 12. Always look up there where it says data type size, and that will give you additional clues. Now in this case this is too simple, you really didn't need it. Okay, so counters, timers. Let's pick a predefined data type that is more complex, such as alarm_analog. Notice the name of the class of objects at the top of this screen capture. It's called alarm_analog, and then it shows a list of the members, and it shows data type size 236 bytes. If you divide by 4, that'll tell you how many dents you have. So 200 divided by 4 is 50, 36 divided by 4 is 9. So you have 59 double integers probably consumed to create this tag. Now if you look here, you see 1 real and the rest of them are Boolean. That's because you're not looking at all of them. So let's look at the rest of them. Okay, that was the first group. See, it went down to operator unsuppress, and we start with operator unsuppress at the top. There is more, and notice that they are not in alphabetical order. However, it was nice of them to at least put some order, such as high descending to low, as you see here. So you've got high limit, high severity, high limit, high severity, low limit, low severity, low limit, low severity. And then if you look down towards the bottom, you're going to see high in alarm, high in alarm. And if we go to the next screen, high in alarm, well, I started with the same tag just so you could see that it's continuous. So you had high, low. And you see that again where it says acknowledged, HH acknowledged, H acknowledged, and so forth. Then you look down a little further, HH in alarm unacknowledged, etc. Look down a little bit further, high in alarm time, high alarm count, high in alarm time, high alarm count, low in alarm count, and then it'll go all the way down to low alarm count and low in alarm time. So at least they put some of these in some order. But there's more, and a little bit more. This is just one of the predefined data types. We also have module defined, which we discussed in depth in earlier lab projects, so we're not going to repeat that. Notice that there's no plus sign there, because when you first open up a project, you have not added any modules to your I/O structure. When you add them, then the templates or the class of objects for that particular I/O module will pop up here under module defined. You have a plus sign there. And then of course we have strings. I think everybody knows what a string is. A string is an array of ASCII characters. And as you know, ASCII characters usually consume 8 bits or a byte. If you look down below there, you'll see that this is stored, ASCII is stored, of course, in 2 bytes, single integer. It's stored in single integers, which is a byte. But Rockwell does not call their single integers bytes. But it's also inferred that it's in ASCII. So if you look at this string structure here, it has a double integer for a length, and then it has data, and the data is an array of single integers. And here they show you that you have 88 bytes for data size, but only 82 single integers. But you're not limited to 82, an array of 82 single integers. When you actually right-click on strings and create a new string, you define the length. or I should say you define the size of the array. So anyway, we're not going to do strings in this volume. We'll save that for volume 2 or volume 3. And of course, until you create an add-on instruction, you do not have any add-on data types. Okay, so let's move on to the specifics of the lab project. In the actual lab project, the first thing we did was to have you create a new project and name it data types. I see that I didn't put an underscore in there. It really doesn't make any difference, but just so it looks just like yours. And then, of course, you pick whatever hardware you're working with, whatever revision software you have, and then make sure that you create it in some place that you know where to go to look, to find it, so you can browse and then point to a specific folder to save it in. Data types, data structures, backing tags, information objects, if you like, are values of qualitative and quantitative variables belonging to a class of items. Data in computing or data processing are usually, and by the way, data is plural and singular, are usually represented in a structure, often tabular, a tree or a set of nodes with a parent-child relationship, or a graph structure as a set of interconnected nodes. I know that's a long-winded explanation, but that kind of grabs everything. In computer science and computer programming, which is what we're really working with here, a data type is a classification identifying one of various types of data. Rockwell calls this initial class, and we went through this just now in the earlier part of this presentation, as atomic data types. And of course they have various data types such as real or floating point, long integer, double integer, integer, single integer, and Boolean. These classifications determine the possible values for that type. So if you take a single integer, that's 8 bits, and you treat it as a single integer, then it's 0 to 255 in decimal, or it can be any one of 256 different symbols for ASCII. And of course there's Boolean, which is a single bit. The actual values are implicit in the data type, and the way values of that type or structure can be stored. The types listed in our presentation were the atomic data types. We went through those specifically, and they make up all data structures in the Logix Engine. It is worthwhile to point out again that these data types are confined within the boundaries of a DINT or a 32-bit data type. Therefore, double integers are considered the native data type for the Logix Engine, and everything moves faster and more smoothly with DINTs, double integers. Our only interest in this lab project is to explore specifically what data types are available to the Logix Engine via RSLogix 5000. So we created a new project called data types, said OK. This is something I was working on before I started here, otherwise I would have deleted this so you didn't have to look at it. Do I want to save what I was working on? No. Okay, here's our new project called data types up here. You can't see the title bar. It's just out of your reach because I wanted to maximize the usable space for the screen capture. But anyway, this is the project right here. You can see controller data types. And then we had you go down here and look at the data types. So you can collapse that. You can expand it. If you expand strings, all you're going to get is the template or the class of objects for strings. If you actually want a string instance, you right-click New String Type. And when you do that, you can put in the name of the string, then maximum characters, and then declare it. So you're not, see, here it shows question marks for bytes. Later on you'll see that when you look at the class of objects, it shows 88 bytes. That's because for this little structure shown here, it's 88 bytes. But we're not doing strings today, so let me collapse that. And let's go to Predefined and expand that. And we went through and pointed out all of the atomic data types, which we're not going to do Again, if you look through here, there's a Boolean right there. If you go down, you'll find there's a double integer. There's an integer, there's a long integer, and there's a real. If you click on those, double click, nothing happens out here. Whereas if you double click on one of these others, it pops up with the template or the description for that predefined data type. So if you double click on real, nothing happens because it is an atomic data type. Same thing with single integer. Double click on it, nothing happens. In your lab, I had you compare the data types with that you used in RS500. I actually showed you instances of the data objects in RSLogix 5000 so you could compare them directly for those of you that are moving from 5500 into 5000. And I picked timer and counter data types because most of those are extremely familiar to us. There is only one counter data type and only one timer data type. All timer instructions work with the same structure. There's not a count up counter and a count down counter. There's just counters. And you can instruct it to count up or count down. You only have one timer structure, but you can instruct it with a on delay timer, off delay timer, or retentive on delay timer. Okay, then there was module defined tags. And for module defined tags, we actually had you add a module. So we went down to the 1769 bus right there. See, if you right click there, it's grayed out. Right there's the bus. New module, and we picked, I think, an OB16. So I'm going to type in OB, and I'll double click on that part number. So now I can go in. By the way, let me cancel back out of this. Notice that for module defined data types, there is nothing right there. See? No plus sign. Okay, so we'll do that once more real quick. New module, OB, double click, give it a name, and it's an output card, so DC underscore out puts, and we're going to put it in slot 1, so we'll just put 01 after the name. This is arbitrary. You could call this monkey doodles if you wanted to. So I just try to pick names that kind of fit the module. And we're not going to change this business because we just want to show module defined text. So when I click OK, and voila, see there's a plus sign there next to module defined, and there are the three. I'll click on one, double click on one. These are the three structures that are needed to support this I/O module that we just added. And of course, if I went and added another I/O module just like that, that does not increase the module defined tag classes of objects here. And just to prove that, new module, make it the same one, OB 16P, double click, let's call it more, and we'll put it in slot 3 or slot 4. Okay, of course, if putting 4 there doesn't put it in 4 over here, you have to actually go pick the slot number. So we'll say OK. Now notice we have 2 OB16Ps, but we do not have 6 classes of objects. This is the same class of object, but this class of objects right there, 1769, digital output 16-point configuration, and so forth. Input, C for configuration, I for input, O for output. Okay, so if you double click here, you'll see the only thing in there is an integer that represents the 16 output points for that module. Now, if I go to controller tags, swing that over, look, I1C, 4C. It uses the exact same data type, module defined data type. That data type and that data type are identical. This one and this one are identical. The third one and the sixth one, they're identical. Both of these modules, if you like, use the exact same data structure, but it's two different instances of the same data structure. Swing this up a little bit. See, there's your 3 digital output classes of objects. I had you add an input module, and I'm thinking it was a IQ16F, so I'll just type in IQ. Then I can just double click there, and we call that DC underscore input 02. We're going to put it in slot 2. That just happens to be the next available slot. So you say OK. Now look, we have 2 new classes of data objects in our list here. Here's the 3 we had before, DO, DO, DO. Now we've got one that says DI16 and one specifically for the IQ16F. So to further illustrate that, I'm going to delete that, but notice that these stay there. Now if you export this program and import it into something else, you're going to lose those 2 tags because they really don't exist anymore. So I'm going to delete them because we don't have a module now that's using them. But I'm going to illustrate something here. So I'm going to go back down here. I'm going to add a different module, and I'm going to add an IQ, but I'm not going to pick the F. I'm going to pick the standard. And notice that this time we did not get 2 new classes of data objects. We only got the one, digital input 16 point. We didn't get the other one that was specific just to the IQ16F. Okay, so that's what we did in that part of the lab. I had you then add an analog card, which was an IF4X-OF2. So you go back to 1769 bus, new module, and it was a IF4. So if I type in IF, that basically brings up everything with an IF in it. And our choice is there. If I type 4, it reduces the choices a little bit more. If I put in an X, we're right down to one choice. That's the one we want. You didn't have to go that far. Double click, and this we called analog in out. And we put it in slot 3. Okay, now look, we've added some more. Remember, we had these first 4 right here, digital input. Now we've got IF4X-OF2s. Actually, all 3 of these are specific to that exact part number. If we were to go, and I'm just making this up on the spot, folks. If I were to go and add another input module, only this time we'll make it in IF4. We're just experimenting here. We'll double click, and we'll call it in only. I guess I should be complete about analog in only, and we'll just leave it be in slot 5. Okay, now look, we've added 2 more tags, one for configuration, one for the actual inputs, because this module right here, the IF4, is not supported by these 3 backing tags. It has its own backing tags. So I think you're starting to get the idea here between the module defined tags. These are classes of data structures or data objects. They are not tags. They are not I/O modules. They are the data structures that support these I/O modules down here. So in the lab, I had you go to controller tags and then look through the data type here and compare them to the data types over here. Now, they're not in the exact same order simply because it goes by slot number, slot 1, slot 2, slot 3, slot 4, and slot 5. But you will see all of these module defined data types used over here. Now remember, if I delete a module, for instance, if I delete this OB16P here, that will not delete anything over here. So keep your eye over here when I hit yes. See, now it did jump. That's because it did something on here, but it's still the same number of tags that were there before, which are all used over here. Now there's less over here now because I deleted one of the modules and it popped out of the controller tag database and it's gone. Next we're going to do user defined data types. So let's collapse module defined, let's collapse IO configuration, and we'll go to user defined. Well, there are no user defined data types, so we're going to create one. Okay, the next thing I had you do was to create a user defined data type called tank. So I'm going to start that. I'm going to go over here to user defined, right click, new data type. Go up here and type in tank. Now, tank, I mean a storage vessel. And I think you realized that when you were doing the lab that it did not mean an armored tank or a military tank, but it means a storage tank. I'm going to pause and I'm going to type in the members. Now I'll do one, go down here to name, and I'll type in capacity. Data type is going to be real. And the style is floating point. The description is going to be cubic capacity. Now that's what I had you do in the lab. However, I could put in gallons or cc's or I want. So I'm just going to put in a cubic capacity. Okay, so I've created one member. Now I'm going to pause, add in the rest of the members, and then come back. I'm not going to make you sit here and listen to me mumble and type all this in. Okay, now I have all the members typed in: capacity, minimum level, max level, agitator speed, agitator runtime. Notice I have different data types. I have floating point or real for some. I have double integer for others, integers for some. And I do also have a couple Boolean and a single integer. I forgot to put in this one. That would be a real as well. So I can just type in RE, and that gives me what I need. I hit enter, and it's done. That was one I failed to complete when I was paused there for a minute. You can see all of these tag names or members could have something to do with a tank that is we'll call it a reactive process, or it's a process where you put in several ingredients, and it looks like this tank is limited to 3 ingredients, A, B, and C. These integer values would be the raw material identification number, and that would of course come from your batch software or from a recipe management software. Here we created a data structure called tank, okay, made up of many different data types. Now, least you have forgotten, let's look at RSLogix 500. Here's your data files, and these are your data types, okay? And you are pretty much limited to these. For instance, real would be floating point. If I open that up, I have one value. If I want more, I go to properties and I say, well, give me 10, okay? Now I have an array of 10 floating points or 10 reals. If I needed some integers, double click to open that. Oh, by the way, let me go back here and lock this on top so it doesn't disappear on me. Put that one on top. And let's say I needed 30 of those. So type in 30, apply. Now I have an array of 30 integers. Okay, there wasn't single integers, but there were Boolean. Well, not really. People say, well, binary, that's Boolean. Well, not really. It's 16-bit integers. It's implied that you're going to use them at the bit level. The point I wanted to make here is, if you wanted to use these different data types in Select 500 to come up with something called tank, you had to individually craft each one of these, some specific memory location, and you had to associate it with a tank. You couldn't create one class of objects and then instantiate it every time you wanted to use it. So just a little reminder there of how you used to do it. Okay, so here's our class of objects called tank. I'm going to hit apply, OK. And now under user defined, I have tank. If I double click on it, I can open up and look at it. It's not all grayed out, so that means you can change it. Now it is possible to secure this so people can't change it. We're not going to do that in this lab. Let's go back to our program here. So now, if we were to duplicate our example here of the data, and you were going to do it in Studio5000, you would have to describe and symbolize each member of your tank data. Not once, but every single instance you added another tank to your logic. I've done this type of programming with PLC5s and Studio5000, so I know how tedious it is. Now, there are some shortcuts. You can export and import, you can index your addressing as you import, and you can do a lot of things to save time. But it's still a lot of work, and you got to pay very close attention to what you're doing. And the worst part is, if you did 10 tanks, and then you go, oh, phooey, I forgot to create a tag in each one of these for actual tank pressure, which of course we don't have one in our definition here. So in RSLogix 500 or 5, you would have to go to every single instance of your tank, and you would have to add that additional data to your implied data structure. You don't have an actual data structure when you do that kind of stuff in 5 and 500. It's only implied. It's only in your mind, because you're the creator. You know where your data is scattered around. All the floating points are in one file, all the integers in one file, etc. So now, if we go into our database here, right click, and we type in one that says premix, okay? Premix. And now we're going to define this data type. It comes up as a dent, but we don't want a dent. We want a tank. So I type in T. Oh, there it is right there. Don't even have to type in the A. Hit enter. Now look. Let me expand this. Premix capacity, premix minimum level, etc., etc., etc. Let's see if I had you do any more instances. Yes, I did. I had you create 6 additional tags with the same UDT tank. So I'm going to pause. So we paused, and I typed in, I had premix. See, premix capacity, minimum level. I had mixing 01, another tank mixing number 2, and so forth, buffer tank 1, buffer tank 2. So now, so you see how quickly I created literally a couple hundred tag names, all spelled out specifically for the application. Notice these all say tank right now. Okay, what I'm going to do is I'm going to add descriptions for each of these instances of the data type tank. So I'll go up here to this one, premix with slicer. If you don't know what a slicer is, and I don't mean a bagel slicer for slicing bagels or a bread slicer, there is a type of tank. I see that I got an uppercase R there. I didn't mean to do that. There's a type of tank that has what you might consider an agitator, but what it really is has a really high speed shaft that extends from a motor down through the center of the tank down towards the bottom, and at the end it has what you might call a saw blade, and it could have any type of teeth on it. It might even just be a straight, very sharp edge, and it spins at a high speed. It creates a vortex. It pulls all the material in that tank into the proximity of that spinning disc, and it slices whatever it is that you threw in there. You would not want to fall into a tank with well, I wouldn't want to fall into a tank with anything in it, personally. Not even something that's good to drink. I would not want to be in the tank. So I'm going to go through and name these, but I'm going to pause first. However, I have to unpause because I see I made a big boo-boo here. I typed in this for data type, and it should have been tank, and over here is the description. I got so excited about the slicer that I typed it in the wrong field, but you see it was nothing to fix it. Premix with slicer. I'm going to pause before I do the rest of them. Okay, now you see I've got these all typed in. And of course these names aren't that great. I probably didn't spend a lot of forethought to make this really look like it was well thought out. I just want to demonstrate something very important. Now before this just said tank, right? It didn't say premix with slicer batch 01 mixing. So now when we expand it, notice that we have concatenated, if you will. We have put together the description for the tag premix with slicer, and it's put it in front of the actual description of the individual members. So premix with slicer RPM, premix with slicer batch mixing time. See, so it's put those two together with the descriptions from the class of objects over here. So these descriptions from the class of object have been added to the description for that actual tag structure. So it gives you a pretty decent description. So you can create descriptions in a hurry by thinking through the description for the instance of the tag. The tag is a tank data type, but the instance is premix. And we do the same thing down here. Pick any of these. See? Batch 03 mixing, RPM, batch mixing time, process set point. We probably should have put temperature process set point. Well, let's go do that. Let's see what happens now. So I'm going to go over to here to tank. I'm going to leave this open. Go to tank. And I'm going to scroll down. We'll get rid of that. We don't need that. I'm going to scroll down to right here. And I'm going to add in temperature set point. Then I'm going to go into here and add pressure set point. Now when I open this back up again, look at there. Process temperature set point, process pressure set point. This is inheritance. So I create this user-defined data type, and I think it all through, and I'm really excited about it. Then I sit down and I create 50 instances of it. And then on the 50th instance, I'm smiling, I'm thinking I'm cool, and all of a sudden I go, oh my, I left something out. You see how easy it is to put it in there? You just go add it to the class of objects, and all instances inherit any changes you make to the class of objects. And by the way, the UDTs can be imported in from other projects. That was pretty cool. Any seasoned programmer that has spent years using typical flat database descriptors, which is what you had in 5 and 500. We call that a flat database. There's no structure to it. It's just flat. You have a couple hundred acres of wheat. You have a couple hundred acres of floating point. You have 50 acres of corn. You have 50 acres of Boolean. All Booleans are in one spot. All floating points in one spot. All integers in one point. It's just a big flat database with no correlation other than in the programmer's mind and documentation. That's 5,500 land. In 5,000 land, you have actual structures. So what you're looking at here on the screen, Mexine 03, that is literally a data object somewhere in the memory of the Logix Engine controller. That'll do it for, well, wait a minute, let's go ahead and do add-on instruction data types. That really is part of this lab. So I'm going to pause a minute. The only category of data types that we have not really mentioned is add-on defined. Now, add-on defined only become available if you have an add-on instruction that uses that backing tag. And that data structure gets created when you create your add-on instruction. So what I did was I opened up a project that has an add-on instruction in. So I'm going to go over here to add-on instructions, and I have one called cylinder. And I'm going to open up the logic, and in the logic, by the way, I will drag this over so we can see more of the logic. And good. If you look at this logic, it says if the cylinder is told to extend, see it says cylinder extend solenoid, and the cylinder extend switch is made and then start a timer, a debounce timer for 200 milliseconds. And when the timer is done, then we turn on a bit that says the cylinder is extended. When we turn on that bit, in other words, when the done bit is true, and we turn on the bit that says extended, we one-shot a move instruction, which is really a word copy. We capture the accumulated time that it took to extend the cylinder, including debounce, and we put it in extend DT. Then, as well in the meantime, if it is not extended, then we start another timer. So that timer is going to start right away as soon as you energize the solenoid. Because it's not extended, you're going to start another timer for 2 seconds. And when it's done, it's going to say that it's faulted. Well, what do you mean it's faulted? Well, the extended bit stayed off for 2 seconds. Therefore, it's an extend fault. In the meantime, during the 2 seconds accumulate on that timer there that says cylinder extending, if it does make the prox or the extend switch plus the debounce, then that branch is going to go false and you'll never turn on the fault bit. And then in the third rung, if you want to call it that, or the third branch, if the preset is greater than 0, and we just do this for math reasons, so that greater than doesn't necessarily have to be in there. Anyway, we multiply the preset by 0.75 to get a value that represents 75% of the time that it takes to fault if it doesn't get extended. Okay, so if the accumulated value exceeds that extend warning ET, then we latch a bit that says extend warning. Now notice that the extend fault and extend warning are both latches because we want to keep that fault or that warning even if the cylinder made it in 1 millisecond over 2 seconds and the machine keeps running. We want to know that it's faulted, or we want to see the warning, because that means the operator's messed with the flow controls, the pressure regulator, or something's getting dirty, something's bent, etc. Anyway, so that's just a little piece of code that we threw in to make as an add-on instruction. In other words, all this code you see here is part of an add-on instruction. I'm going to, and we open that up here, Logic, add-on instruction. So I'm going to close that. I'll go to main routine, and here's the actual logic that's using the add-on instruction, and this is an instance of that add-on instruction right here. And if I open up the instruction logic, you're going to see the exact same thing. This is exactly what you just saw. We just went through this. Now, we're not doing add-on instructions today. We're doing data types. So if I go down to add-on data types, double click on cylinder, now you see all of the members, if you want to call it that, of that add-on instruction. So I know that's just enough to kind of wet your whistle, not really give you anything on add-on instructions. But add-on instruction data types are created when you create the add-on instruction. Thank you for watching Data Type, from an introduction to RSLogix 5000 from the complete PAC Learn series.